So let's start with a simple type of function, namely a polynomial. And the one I want to look at is in my problem book 9.5, number 5. So there we have our function. I'll call it f of x, but you can call it y, you can call it whatever you want. Negative 2x cubed plus 3x squared plus 12x plus 2. This is going to be our polynomial. So first, we identify it's a polynomial, and with that comes some properties that I won't have any asymptotes. I don't expect any, let's call them strange things to happen. It's defined everywhere, and I can find a y-intercept as y equal to 2 when I plug in x equal to 0. The only thing I'm left with is this 2. So I also want to make a page where I am slowly going to put information in as I follow these steps. And I'll refer back to this as we go. So we'll have our basic layout here, x and y, and we found our y-intercept to be 2. So I'll put that in over here. Let's call that a 2. Alright. Next is our main step, and because I identified as a polynomial, I know that there isn't going to be much to do in this asymptotic behavior step. In fact, you might feel that there is pretty much nothing to do. But we can say things like, if x approaches infinity, then what does my function do? For that, because it's a polynomial, I look at the leading term. Long term, the function is going to behave like its leading term. And because x gets really big positive, x cubed gets really big positive, negative 2 times x cubed will therefore get really big negative. I like to say it like that. And when x approaches negative infinity, I still look at the behavior of the leading term. That tells me how the function is going to behave long term. Now x is really big negative, so x cubed is going to be a really big negative. Another negative in front will make it very big and positive. So I can indicate that to remind myself that after all the ups and downs are done, the graph is going to go down on the right and up on the left. So as I'm completing these steps, more and more information will get put in the graph, and this is just a rough sketch of all the information that I can clean up later. So, because of the polynomial, there's not much to do in step number 2. So we move on to the next one, which is our increasing, decreasing behavior. And for that, we are going to look at the derivative. So the derivative properties involved here are simple properties, sum difference property, constant times a function, and our main power rule, giving us negative 6x squared plus 6x plus 12. So that is now our function that we're analyzing to say something about our original function. So I want to clean this up and factor it in the case of a polynomial. So what I could do is take out a negative 6x to make it even easier. Then I have a negative x and a negative 2. and then I can factor that as 2 brackets. Now your factoring skill might be different, so we don't want to make it too complicated. We can always FOIL this out and see, do I get the original back? It's going to have to be factors of 2, and my larger one will get a positive. FOIL it out, I get my x squared from the first ones, outside ones an x, inside ones a negative 2, giving me negative x, and the last ones give me negative 2. So that is good. Then I'll do it on the side here. We are checking 2 things in general. We're checking when is my derivative equal to 0, and when is my derivative undefined. Now in the case of a polynomial, the second one is going to be a never. No values of x will make this function undefined, but I do get a couple when x are certain values, in this case a negative 1 and a 2, that will make the derivative 0. So these are my potential critical points at this stage. Then I like to make a little table to see how do these factors affect the eventual sign of my derivative. So we're going to mark off all these potential critical points, negative 1 and 2. Some call them critical numbers. And I'm going to list on the left here all the pieces, all the factors that go in making my derivative. Together, by way of multiplication, they will give me the first derivative. And I've broken up my x-axis into these pieces, these 3 intervals. Now negative 6 is always going to contribute a negative number. X minus 2 is 0 when x is 2. And because it is being multiplied in my derivative, it will make the derivative 0 as well. X plus 1 is 0 when x is negative 1, makes the whole derivative 0 as well. X minus 2 on this left interval is going to be negative, another negative, and then a positive for all these x values. Now, it's a familiar looking expression that you might get used to, or you can plug in some representative numbers here, maybe a negative 2, maybe in between will be a 0, and in between an easy number is a 3, and whatever it does for that x value, it'll do for the whole interval. X plus 1 is going to go from negative to positive. Now I have 3 negatives. For any of these x values, it will be 3 negatives multiplied together to give me a negative value for the derivative. In the middle section, 2 negatives will make a positive, and in the last section, 1 negative will make a negative. So I can draw my slope lines to illustrate this further. I'm going to have a negative slope, and then a horizontal slope for my tangent line, and then a positive slope, showing that little cup shape that is going to happen in the graph. For the next one, as I pass through x equal to 0, I'm going to get a positive slope, 0, negative slope, showing that crest that is going to happen in my graph. The last thing I might want to do is to list the critical points. Now, critical points, I have to have an actual point on my graph. My function has to be defined at these x values, but they certainly are for both. My function is defined. I just need to find the corresponding x values. Alright, so when x is negative 1, we want to find the corresponding y value. And for that, of course, we look at the original function. When you plug that in on your calculator or do it in your head, you get negative 2 times negative 1 cubed plus 3 times negative 1 squared plus 12 times negative 1 plus 2, and you should get negative 5. Oops, that almost looks like an 8. It's a 5. Then, when we plug in x equal to 2, so sorry, this is negative 5. That's our first critical point, because it comes out of my list here that I'm checking, and there's a point on the graph. The function's defined at the x value. Then, when x is negative, or not negative 2, when x is 2, we'll plug that in into your calculator or do it in your head, whatever works for you. Negative 2 times 2 cubed plus 3 times 2 squared plus 12 times 2 plus another 2, and we get 22. So our next y value here is 22, giving us our second critical point. We can then wrap this up with a sentence saying f is increasing on the interval negative 1 to 2, and f is decreasing on negative infinity to negative 1, as well as, I'll squeeze it in here, 2 to infinity. So if we want to put that in on our graph, we want, so increasing on negative 1 to 2. Let's first put the critical points in. Critical points, negative 1, 5. So I'm going to zoom this in just to make the shape easier to draw. So negative 1, negative 5. Let's put that over here. And at that point, which is this one, I'm making a little cup. So I'll remind myself of that. Then at 2 and 22, I'll abuse the scale just for convenience of the shape here. 22, I have my little crest happening there. It's increasing in the middle section, which makes sense because I have to get through my y-intercept. And then it's decreasing as I come to that and decreasing past that. So the shape is starting to form very nicely. Please remember to click the like button if you enjoyed the video, and to subscribe if you want to be notified of more videos. Thank you.